In this lesson, we are going to talk about the Bohr's model of the hydrogen atom, second part of the chapter Electronic Structure of Atoms. We begin by the outline of this lesson. So we first start by the emission spectrum. Also, we give the Bohr's postulate. We'll talk also about the energy levels in hydrogen atoms, and we finish by talking about the emission spectrum of hydrogen-like ions. As learning objective, at the end of this lesson, we'll be able to understand the origin of the atomic spectrum from an energized gaseous pure substance. We start by the emission spectrum of white light. We all know this experiment where white light from the sun, for example, passes through this slit and goes through this prism. What happens is that this white light will be separated into different colors of the visible region, as we can see here. And here we have a continuous spectrum. So from the white light, we get a continuous spectrum. However, if we replace this light by, for example, a light that comes from a simple pure substance of hydrogen, like we have here, we have a vacuum tube which contains hydrogen gas, a pure substance. If this hydrogen gas is energized, red light will be emitted from this vacuum tube. This red light, if it goes through this slit, and also it will pass through this prism, it will also be decomposed in different colors. However, conversely to the white light, here we don't have a continuous spectrum. Instead, we get bright lines, as we see here, the red light, the green, the blue, and the violet. Here we have a line spectra. So from the pure substance, from the hydrogen atoms, we get line spectra. So it is different from the continuous spectrum from the white light. And here notice that each color, it has its specific wavelength. For example, for the red color, we have 656 nanometers. And this line spectra is unique to this substance, which is the hydrogen gas. If we change the element inside this vacuum tube, we'll get a different emission spectrum, as we can see here. So for the helium, we have always bright lines that are not continuous, but with different wavelength. The same thing for the nitrogen, oxygen, and the other elements. So it's like a fingerprint of that element. At that time, it was difficult to explain these bright lines. Why elements emit these lines instead of a continuous spectrum? A second question that was also difficult to answer or to explain from the classical physics at that time. According to the Rutherford's model of the atom, the electron, which is negatively charged, orbits around the nucleus that is positively charged. So why the electron doesn't collide into this nucleus, as we can see here? So it became clear that the classical physics at that time was unable to answer these questions, and Niels Bohr in 1913 introduced these important postulates, which says that the electron is allowed to occupy only certain orbits of specific energies. So electron is not allowed to emit energy, and also the electron emits radiation only when it transitions between the different orbits of different energy levels. To understand better this postulate, we'll talk about this experiment where the hydrogen gas emits radiation when it is energized. So we can see here that we have a red light, and here we have the emission spectrum of the hydrogen atoms. So according to Bohr, this line that we see here is due to the transition of the electron from the orbit number 3 to the orbit N2. And this green light is due to the transition of the electron from the fourth level to the second level, and this third line is due to this third line results from the transition from this orbit N equals 5 to this orbit. So each time that an electron moves between these orbits, it will radiate energy. So because the electron couldn't be on any energy level and it has to emit only energy of a given wavelength, so it became clear that energy of the electron in the hydrogen atom is also quantized. So according to Bohr postulate, energy is quantized. Because the energy it has to occupy only orbit of specific energy. And the energy of the electron in the hydrogen atom is equal to so here we have the energy expression of the electron. It is written as minus RH. Here we have the Rydberg constant. It is the Rydberg constant, which is equal to 2.18 times 10 to the negative 18 joule, or in EV 13.6 electron volt. The N here, it is a positive integer, so it can be 1, 2, 3, and so forth until infinity. Now let's talk about this orbit. The first orbit that is related to the N equals 1 is the closest one to the nucleus. When the electron is in this orbit, we say that the electron is in the ground state, because it is the level where the electron is the most stable. After that, if the electron is in the orbit of N is equal 2 or N equals 3 and so forth, we say that the electron is in the excited state. When the electron is beyond the infinity, we say that the electron is free, or the electron is removed from the atoms. So when the electron is close to the nucleus, the stability will be higher. But when the electron is not close to the nucleus, we understand that the electron will be less stable and easy to remove from the atom. And it is easy to see that for N is equal to 1, we have the energy of the electron, which is equal to minus the Rydberg constant. But when N is equal to infinity, here we have the energy of the electron, which is equal to 0, because 1 over N to infinity is 0. Now let's talk about the emission process in the Bohr's atom. So according to this model, when the electron returns to a lower energy level, it will radiate energy in the form of photon. Here we have a photon that is emitted, and it has an energy that is equal to h times nu. Here we have the Planck's constant and the frequency of this photon. And here we have the transition of the electron from the N initial, which is equal to, for example here, which is equal to n3, to n final, which is equal to n2. And here we have the energy level of the third energy level is higher than the energy of the second level. Now let's talk about the energy needed in this emission process. So as the electron moves between two different orbits, we'll have a difference in energy, which will be equal to delta E, that is equal to final energy minus initial energy. And here we have this final energy corresponds to the final n, and the initial energy corresponds to the initial n, or the number of the orbit. And here we have this relationship and the expression of the energy that is emitted after this transition is written like this. So here we can see that the energy can be either negative or positive. It depends of this orbit. So if the n initial is greater than the n final, we'll get a negative energy, which means that the energy is emitted. Here we have an emission process. But if the initial n is smaller than the final n, so we'll get a positive energy, and here it corresponds to an absorption process. We'll talk about the absorption process at the end of this lesson, but now we will focus only on this emission process. Because the energy is emitted as a single photon of energy h times nu. So how can we get the wavelength of this photon? We just make the difference energy that is equal to h nu. So, and we know that the frequency is equal to c over wavelength. So we can calculate the wavelength of this photon through this relationship. Here the Planck's constant is in joule second. The speed of light is in meter second minus 1, and here is in joule. So we can cancel joule second, and at the end we get a value in meter, which corresponds to the wavelength of the photon. Let's do this example. In this example, we have a photon that is emitted during this transition from the initial state n equals to 5 to final state n equals 2 in a hydrogen atom. We are asked to calculate the energy of this photon in joule and in electron volt. So we have a photon that is in the fifth level. So we have here the ground state, second level, third, fourth, and fifth level. The electron is in the fifth level, which is the initial state. And this electron will move from the fifth level to the second. So here we have the electron that will be moved between these two levels. And as it returns to the second level, it will emit energy in the form of a photon of energy h nu. Here we have an energy of a photon. This level corresponds to the final level. So here we can see that the initial n is greater than the final n. And because here we have said that when the initial n is greater than final n, so we have an emission process where the difference in energy level will be negative. So we can apply this expression to determine the energy that is emitted, or the energy of this photon. So just we replace, we have here delta E that is equal to joule times 1 over 5 square minus 1 over 2 square. If we make the calculation, we'll get the value of minus 4.58 times 10 to the negative 19 joule. And in EV it gives a value of minus 2.86 EV. So we see here that it is a negative value because it is an emission process. So we have the value in joule and in EV. The second question, what is the wavelength of this photon in nanometer? So the energy of a photon is equivalent to this relation, so which is equal also to h times c over the wavelength. So we can determine the wavelength of this photon using these energy values, which is equal to h times c over delta E. And here we have just to replace the Planck's constant, which is equal to 6.63 times 10 to the negative 34 joule second, times the speed of light, which is 3 times 10 to the 8 meter second minus 1. Here we take the value in joule. So we can cancel the joule second and we get a value in meter, which is equal to 4.34 times 10 to the negative 7 meters. But here it is a very small value, so we have to convert to the nanometers. For example, we know that 1 meter is equal to 10 to the 9 nanometers, and we get a value of 434 nanometers. So here is the wavelength of this photon. And this photon, because it is between the 5th level to the 2nd level, we have here, it should correspond to this line, which is from the 5th to the 2nd orbit. And here we are asked to which electromagnetic region does the photon belong to. Here it's easy because the visible region starts between 402 and ends at 800 nanometers. Here we have the visible region. So this photon must belong to the visible region.